last lecture, we just started to discuss the tropical zonal and meridional circulations. The idea is that in the lecture before, we were mainly focusing on the zonal mean picture, which gave us insights into the Hadley cell, into the Ferrous cell in the exotropics, and so on. But they're also important, and we know this already considering ENSO, deviations in the zonal direction from the zonal mean. So things are a little bit more complicated. And so we have looked at this figure with the rainfall distribution in shading here. This is for boreal summer season. And yes, we see that there are asymmetries in the zonal direction. And particularly if we look at the equator, we see that in the Eastern Pacific, it's almost dry. In the Western Pacific, it's raining a lot. And this is the background state on which also the El Niño phenomenon then develops. But in this lecture, we want to discuss again the more like mean state features and how this mean state feature here may be influencing the distribution of monsoons, and particularly in the South Asian region. But we have to discuss first a very important equilibrium. So we have introduced already the stream function, here the velocity potential, which just is the gradient of the velocities are the gradient of the velocity potential. Whereas the stream function is defined as just the rotational part. So we can define our rotational winds by vertical unit vector cross product with the gradient of the stream function. So our geostrophic wind was defined through a stream function. And in fact, we will interchange these two. This is essentially the geostrophic wind. We have to be a little bit careful if we go too close to the equator. But as soon as we are a little bit away from the equator, this can be interpreted as a geostrophic wind. So we looked as an example of this already, what is the upper level, so at tropopause level almost, the mean state for the velocity potential. And because of the sign convention, there's this huge negative anomaly in the Western Pacific, because we have this rainfall. The stream function response. And looking at this lower panel here, which is also the upper level stream function, in this case, ESP-AD stream function distribution, we can see that there is a clear relationship between these two. And so this is what we want to discuss today. Why is this the case? Is this just by chance, or is there likely to be a very clear relationship between the two? And there is one. And this is the interesting relationship that we want to derive today. So if we go back to our vorticity equation in the pressure coordinate system that we have used already many times to derive Rossby waves in the exotropics, that was this equation. So for pure Rossby waves that don't decay or increase in time, we have used this equation to derive the characteristic equation of Rossby waves, the advection of the relative vorticity and the advection of the planetary vorticity. Those govern, in principle, Rossby waves in the exotropics. Now, that was fine, that's okay. And mostly we have ignored this divergence term. But the divergence term had to be taken into account if we want to derive baroclinic instability. So the growing, if Rossby waves grow, then this term becomes important. Or orography can cause this term, or heating in the tropics, for example. And now we are going now to the tropics. And in the tropics, we will make a very similar approximation to this equation to what we did already to the thermodynamic equation. This is often referred to as weak gradient approximation. So we assume that in the vorticity equation, these are just, as you know, the horizontal advection terms and the time derivative. All those terms are small compared to the other terms. So the horizontal gradients in the tropics are supposed to be small compared to other ingredients in this equation. This comes back to this weak gradient approximation that we have done already in the thermodynamic equation. So the first order approximation of this equation in the tropics is very different to the one in the exotropics. So in the tropics, let's say between -30 and +30, this term may be neglected compared to this divergence term, that because we have all these divergent sources because of the diabatic heating, this term becomes so dominant. And then also this term remains a relevant term. So the first order approximation we get in the tropics is this equilibrium here, which gives us a relationship, because we know that the geostrophic wind is defined through the stream function, the geostrophic stream function. So this gives us a relationship between the stream function flow, the rotational flow, and the divergent flow. And this is something non-trivial. This is not necessarily the case, but this equilibrium tells us this should be the case approximately. And this is a very famous equation. I don't know if you've discussed this already in your ocean course, but that course, has it started already? No. So you will definitely derive a very similar equation for the ocean case. And this equation is in fact named after an oceanographer. So it's called Sverdrup balance. You can reformulate, as you know, this divergence term also in terms of vertical change of the vertical velocity. But for our purposes, it's best to keep this term as it is right now. So this equation is called Sverdrup balance. And in ocean dynamics, this is a very, very important equation. But also for the atmosphere, this is an important equation, because this tells us now, oh, there is a relationship between divergent wind and the rotational wind that is governed by the stream function. So, and if we go back to this figure, where we have this divergent outflow in the Western Pacific over this, where we have the maximum heating. What do we expect from this equation? So we have a positive divergence there. A positive divergence, F is positive north of the equator at least, if we are concentrating for north of the equator. That means that the wind, the rotational wind, should be negative. And so we should get a rotational wind component that goes in this direction. On the other hand, where we have the upper level convergence, like for example in this region here, we expect the opposite direction of the rotational wind. So what we see here in the stream function, and we know that by the definition of the stream function, the wind should go around like this. So this what we have just derived is consistent with this rotation in this direction in the South Asian region, for example. And then we have the opposite rotation here in the Pacific, in the more Eastern Pacific, Northern Eastern Pacific region. So that would be consistent. And in fact, it will be an exercise to show that it is consistent. So in an exercise that you will do, you will insert into this equation an idealized divergence field, and you will show that then the stream function field has to be exactly out of phase. So they behave like if we insert a cosine as a function for the divergence, or it's a function in this case for the velocity potential, we get a sine curve for the stream function. So they're exactly out of phase. And that relationship is, you will show in an exercise. It's very easy to show. You just have to insert it into this equation. So this gives us an important and non-trivial relationship. Now this argument has been used to say, so how the global monsoon systems are related, and particularly how the South Asian monsoon is related maybe to the Western Pacific heating maximum. Because if this is the case, if a large part of this what we call also the South Asian monsoon high is actually directly related to the Western Pacific heating, then that should have important consequences, because at low levels, as we have discussed already in the tropics, the circulations are very what we call baroclinic. So at low levels, everything changes sign. We get, instead of divergence, we get convergence. And therefore, in the South Asian region, we would get a low pressure over more or less this region. And that low pressure, as we know already, due to the Ekman convergence, would suck in then the winds, cause rising motion, and increase the monsoons. So what was speculated then is that part of the monsoon circulation over South Asia may be actually driven by this Western Pacific heating maximum. And that goes a little bit, supplementary or complementary to the standard monsoon hypothesis, which is saying that the South Asian monsoon is mainly driven by the land-sea contrast in the Indian Ocean. So in the it's in the South Asian region, because in boreal summer, most of the heating will be taking place over the continent, because the ocean has more inertia than the landmass, and so the landmass will heat up quicker than the ocean. So in some ways, the Indian monsoon or the South Asian monsoon is considered to be like a giant land sea breeze. And therefore then the air that is also affected by the Coriolis force, but in principle is forced to move from a higher pressure located over the ocean to a lower pressure located over the landmass, and it's converging there and causing rainfall. That would be the canonical monsoon theory. But there's more to it, because that seems to be reinforced by this heating maximum that we have also just over the ocean in the Western Pacific. And a few years ago, we have tried to analyze this again with very similar simulations that almost go back to these aquaplanet simulations that we have discussed already. So in the real world, you can only look at the data and say, yes, yes, these two fields are consistent with each other. But that doesn't tell us yet causality. That just proves that this equilibrium, the Sverdrup balance, is valid to a good approximation. But that doesn't yet tell us what is the cause and the effect between these two, and how relevant the stream function response over the South Asian region is compared to other mechanisms. For sure, other mechanisms would still be the land-sea contrast that is apparent. So, but in a model, you can do something crazy again. You can just remove the east-west gradient in the sea surface temperatures. So we expect that should remove the east-west gradient in the Walker circulation and in the in the heating in the Western Pacific. That should redistribute. And then you can even go a step further. You can, of course, remove again orography and land, and just leave the South Asian continent with its observed sea surface temperature distribution and landmass distribution, but remove everything outside. So really a very, very idealized experiment, just to understand what is the outside contribution to what's going on regional here. And if one does this in a model, you can indeed, this is now the response of this, of looking at this is what we call zonal experiment, or the zonal experiment with even no continents, with respect to the control experiment, which had everything included, sea surface temperature variations as observed, and land sea contrasts as observed. And as you can see, there are obviously changes in the other ocean regions, but even in the Indian region, in the South Asian region, there's a huge redistribution of rainfall. So there's much more rainfall south of the equator in this new experiment where we have kind of removed the east-west contrast, and much less rainfall to the north. So the southern part of South Asia becomes almost dry. And the reason is, of course, as we can guess already, since we have removed in these experiments the Western Pacific upper level divergence maximum is already almost very much reduced in this experiment, but even further reduced in the experiment where we have essentially no east-west contrast anymore, apart from the South Asian region itself. And then that has enormous consequences for the stream function. Because if we look at the response in this model simulation of the stream function, after inserting this zonal symmetry as respect to before, we see that now the values are strongly negative. That means that in this region, this South Asian high is strongly reduced. So there is still some kind of monsoon high driven by the land-sea contrast, but is much further to the north. So it's only the northern part, really, at least in this model simulation, that is driven by the land-sea contrast. But the southern part is very strongly connected to the Western Pacific heating maximum. So that gives us some idea about the interconnectivity in the monsoons themselves. So the rainfall patterns that we see, they are all interconnected. It's not that we should treat what is happening in the Western Pacific independently, for example, with what is happening over the South Asian region, but they are strongly interconnected. They may also, other monsoon systems may be interconnected, but it turns out that the strongest feedback here is actually from the Western Pacific to the monsoon, and perhaps vice versa, but this is more difficult to show in principle. So that was to indicate that the importance of these east-west contrasts. And as an exercise, you will, as we discussed already, you should do a very simple exercise, but it's very useful. To insert into the Swerdrup balance this simple cosine wave. Just assume that we are just looking at the x direction. We ignore the meridional distribution. Just a cosine wave in the zonal direction, and you will work out what is the solution then for the stream function, the zonal distribution of stream function. And you will see, of course, that is also a phase, so goes with the cosine. So you will show that for the zonal direction, what we have observed in this, for these observations, is actually the case if you apply the Swerdrup balance. This out of phase relationship can be explained by the Swerdrup balance. Now, we have to move on with our lecture. We will discuss part of the energetics of the general circulation. That is quite a complex issue, but it's very important because we have seen already there are some weird things going on in the general circulation. When we looked at the jet in the exotropics, we found that that the energy, if the waves transport energy away from this jet, at the same time they transport momentum towards the jet and support the jet in terms of momentum. So there were kind of some weird things going on in for the exotropical energetics, let's say, if we look at the general circulation. And we want to look into a little bit more details into this general circulation. So, but, you know, there will be a lot of equations, but the basic principle is very, very simple. We can explain this if you look at this sketch here. Assume you have just a tank of water and there's a separation. So one of the compartments of the water of this tank has cold water and the other has warm water. Now we take away the separation. What will happen? Can someone guess what will happen here? Sorry, maybe you are muted, or it's me that I muted you. Can you say again?
No, I was thinking that it will stay like the same for a time, and then it's going to start like in the middle. They are going to start mixing slowly.
Yes, okay. That is a very good thought, I think. But this is not what's going to happen. That would, let's say this is, okay, I didn't specify the fluid. But what you said could probably happen if we look at an extremely viscous fluid. But if we look, let's say, at water, something else would happen. And what you say is in principle not wrong, but if we have a very, very, not very viscous medium, something completely different would happen. Can someone guess? No one has a guess? So the cold water would try to flow like this, and the warm water would try to be on top, because cold water is heavier, no? Would try to go to the bottom. So what would happen is you would have kind of a permanent oscillation, not permanent, but you would have an oscillation, because when the cold water goes down here, the warm water goes up, that would release, and this is the main thing we discussed today, some of the available potential energy that is kind of stored in this situation would release into kinetic energy, but then it could go back. So if there's no friction, for example, then that would go completely back again, and everything would be stored in the potential energy. But then that is unstable, and so we would have this oscillation between that makes energy conversion between what we call potential energy or available potential energy and the kinetic energy in this situation. So just like a spring that is oscillating, we can have this oscillation in the basin. But then there's surface, there's friction going on, right? So if we observe this for a long time, what will happen in the end? If surface friction has kind of removed all the kinetic energy that we have, what would be the final state? What would be the stable final state of this? Before what you said, the molecular diffusion can play a role. Before that is the case, something will happen. What will happen? After friction has removed all the kinetic energy. We will have the warm water on top of the cold water. That will be the final situation. after the system has lost all its kinetic energy. The cold and dense water will stay down, and the warmer and less dense water will stay up. That going from here to there has released kinetic energy. Now, where has this kinetic energy gone? It has been lost through surface friction, also friction in the water itself, not only at the surface, but everywhere, essentially in the water. And then what you say may come into play. At some point now, if we wait long enough, but for water, we probably have to wait a few days, probably, then we can have the possibility of exchange, of course, molecular exchange. And then maybe in the end, we will have just one temperature. But for that, probably we would have to wait days, is my guess, even in a small tank. But first, what would happen is this more mechanical phenomena. So we would release the available potential energy in this initial situation. That would lead to kinetic energy, which is dissipated. And in the end, we would get to this state, which then could, by molecular diffusion, be reduced. So we can have a completely stable situation where the colder water is below the warmer water. So a kind of a vertical stratification without any available potential energy anymore. There's no way, once we have this situation, apart from molecular movement, that could lead to macroscopic movement of this fluid, because it's a completely stable situation. This is essentially the basic ingredient that we want to derive now for the atmosphere. For the atmosphere, things are a little bit more complicated because we don't have just a fluid. So things are compressible and so on. So we have to look at the equations. But in principle, if you keep this in mind, we have understood already basically everything. So don't get scared of the equations. This is actually the topic of my PhD thesis. So I went quite deeply into these equations, and therefore I found them and used them in this lecture. But the basic ingredient, if you remember, is just this. And we will come back to this. So for the general circulation of the atmosphere, you may think this is here the equatorial region, and this is the exotropical region. And so that situation also contains available potential energy. And we'll try to get into this situation to release that available potential energy, to gain kinetic energy. And we will come back to this later on. Also, yes. So the rising of the warm air, the sinking of the cold air, everything of this will be ingredient of what we'll discuss later on. So in order to derive energetics, we know that our starting point is always the momentum equation. So this is now the full momentum equation, again, for three-dimensional flow. This is the same equation that we have used to derive the potential vorticity conservation law, the general one. And the frictional forces are just written in a way that indicates that momentum by frictional forces cannot be lost, can only be transferred to another medium, but cannot be lost. So therefore it's written as a convergence of a tensor, nabla times a tensor, scalar product with a tensor, which gives us a vector. So otherwise we could simply write as a vector for the friction, but this should indicate this. Now, how do we derive from this the equation for kinetic energy? We multiply this scalar with the velocity itself. then after reshuffling terms, and this is well known from physics, you get to the equation for kinetic energy, where the kinetic energy is, of course, 1/2 V scalar product V itself. So V square. So U square plus V square plus W square. Okay, this is the equation for kinetic energy. We can write this a little bit different, because noting that this here, after multiplying the momentum equation scalar with V, since we know that this is the geopotential is just G times Z, and nothing there depends, Z is an independent variable, so that doesn't depend explicitly on time. So you can write this is just without the minus sign, just d by dt, it's just reformulating. Of phi, because phi doesn't depend explicitly on time. So that's just the advection of our geopotential. So for the vertical direction, as we know, it gives us our acceleration due to gravity in the end, because it's just G times Z. If we calculate the derivative of that, that gives us just the unit vector in the vertical direction. But we don't have to do this. So with this, we can bring this term on the other side, and we can write rho times kinetic plus geopotential, or potential energy. In this case, it's not geopotential, it's potential. It's really the potential energy that we have here, is equal to, and then we can combine some terms. This term here, this formulation of double scalar product, means that you calculate this by applying the matrix F to the matrix gradient of velocity. So gradient of the velocity gives us a tensor also. You apply the matrix product between the two, and you calculate the trace of that. That's the meaning of this double scalar product. So that's just a scalar in the end, because the kinetic energy is a scalar. Of course, then this, we know that energy, there should be a conservation law, right? Energy is a conserved quantity in principle. So it can be exported or imported, but it shouldn't just be, there shouldn't be loss or gain terms for energy. Energy has a global conservation law. So there must be something missing here. And what is missing is, of course, the internal energy. If you look at the internal energy equation, in this case written down for simplicity for the time being for a one-component system, but we know eventually we have to extend this to at least to allow for the condensational processes that are happening in the atmosphere. Condensational heating will be very important, but for the time being we don't do this here. Just think about if a one-component system, or one-component gas, in this case, then the internal energy equation could look like this, where J could, in that case, if we don't include heating, condensational heating, then this J could include radiative fluxes and just diffusion of heat. So that could be included here. Then we can see how these terms interact. So there is a reversible conversion term, which is this P times divergence term, which can go both directions, which can convert internal energy into kinetic and potential energy and vice versa. This is our work, the mechanical work term that you have been studying in the physics course, in the atmospheric physics course. But then there's this irreversible term, the frictional heating. So when we have frictional dissipation, that doesn't go away. That goes into heating of the atmosphere. The minus sign here doesn't make any sense, but it makes sense because it turns out that this term is always negative. So this has just this direction. Always goes from the kinetic energy into the internal energy. This is a completely irreversible process, whereas this term here is reversible. So if we add these two terms up, we can see that the change of the total energy can only be due to fluxes. So if we integrate about a closed system, and yes, we make it closed, so we don't allow for radiation to come in or for anything else, then we would come to the conclusion that the sum of internal plus kinetic plus potential energy is constant in our system. Now, the atmosphere is not a closed system, of course, as you know. It receives energy from the sun. It's an open system. If it was a closed system, very boring, because we would in the end we would go into the entropy increased death, because in a closed system at some point the entropy will reach its maximum and there couldn't be any movements, any motion anymore in such a system. So of course the atmosphere is an open system, and therefore there can be exchanges of energy with the environment, with the outside of the Earth. But still, we have to take into account that in principle, the energy has to obey this conservation law, and that has to be included by the fact that all the energy, if we add up kinetic, internal, and potential energy, can only be exchanged with the outside, but cannot be generated. So now the key question is, if we have an initial situation in the atmosphere now that is a little bit like this, we may have a real distribution now, less idealized, let's say, but in principle this is what we have. We have a warm equatorial region and a colder exotropical region. We can measure those temperatures. Now, how much energy can we gain from that to transfer into kinetic energy? That is the basic question that, for example, Lawrence in the 1950s asked. So, how much energy can be gained? And it's clear already that a constant temperature, this tells us basic thermodynamic, the Canoe process, a constant temperature will not give us any energy available for conversion into kinetic energy. But even a constant temperature would have a huge internal energy reservoir. So if you calculate CV, the specific heat at constant volume times the temperature, you would get to values per Kelvin, per kilogram, that are of the order of 2 × 10⁵. But if you look at typical values in the atmosphere of kinetic energy, you come to values, we have said, typical value for kinetic energy is about 10 m/s for the general circulation. So at one specific location, that would gives us a value that is about 10⁻², joule per kilogram in this case. This is now in a mass specific or volume specific point of view. We can exchange this. So much less than we would guess even for this trivial case of a constant temperature. So the internal energy is not a good estimator for how much energy we can gain. And of course, this is a very old question from engineering thermodynamics. How much energy should we be able to gain out of a situation? Now, in the laboratory, those questions have been solved many, many, many years ago, hundred of years ago, for idealized, very controlled experiments. So Canoe and other scientists at that point, they have derived those theory. But for the atmosphere, since the situation is more complex, it's a little bit more difficult to derive the very simple laws, how much energy can be gained if we impose some kind of temperature difference. From engineering purposes, we know that if we can control certain situations, then it's very straightforward to understand. Every heat pump, if many heating systems now are based on a heat pump, where you make use of the difference between the external air temperature and the ground temperature, and that temperature difference can make you gain energy. So you use that to gain energy to pump heat into your houses and so on. So that is well established from thermodynamic. If you can control the situations thermodynamically well, but for the atmosphere, we can not really control what is going on. The temperature variations are just as they are. So we have to look a little bit in more details into this. Actually, you come to the same conclusion even if you look at the potential energy, because it can be shown that the global integrals of potential and internal energy, they're just proportional to each other. And this is a very nice exercise that you will do as homework. You will show that potential and internal energy, they're just proportional to each other in the global integral. So internal and potential energy in the atmosphere cannot be really very well used as they are to derive anything that is available. And even if you say, okay, it must be then changes in temperature that are important. But then you have the problem, okay, but that could be even negative. But we know that we can always gain something out of a temperature gradient. So it's not so straightforward how to derive an available energy concept. Now we can reformulate these two equations that we have been looking at a little bit by bringing the potential energy change again here on the other side in the kinetic energy and adding a zero in the internal energy equation. So we simply add on both sides d phi by dt. And then we get to this equation. So we have brought, now we say, okay, we isolate the kinetic energy. But this again, if we add these two, we get to the same results as before. That the energy of the whole system can only be changed by changing from the outside, by changes from the outside, by fluxes from the outside of energy. There cannot be any internal gains of energy. And then for the purpose of this lecture, it's convenient to introduce the entropy change here on the right-hand side, where the entropy for the atmosphere would be just Cp ln theta, as you know, the potential temperature. Now this formulation has something useful because you can see from this way of formulating that if the atmosphere, or at the moment we didn't make any use yet of the medium we are looking at really. So also the water, for example, that we are looking at. If that system is an exact hydrostatic equilibrium, gradient P is equal to minus rho times gradient phi. That is our hydrostatic equation. In the vertical direction, that would look like dP by dz equal to minus rho, that is not good, rho times dz by dz, d by dz g times z is just our g now. So that is the vertical direction. In the horizontal direction, you would just have get rid of this. So we will simply have d by dp, dp by dx. And there's nothing on the right-hand side because the gradient of the potential energy is just in the vertical direction. So that's 0. So if we have no, and the same would be in the y direction, dp by dy. So if we are in this complete hydrostatic situation, then there can be no energy exchange between the reservoir of internal and potential energy and the kinetic energy. And that was our final state here, for example. This is a state where we have no horizontal pressure gradient. Here we had horizontal pressure gradients induced by the temperature changes in the horizontal direction. But in this situation, there's no horizontal pressure gradient. So there's no way we can convert any energy there. So given that there's a hydrostatic equilibrium, we cannot gain any kinetic energy out of the reservoir of internal plus potential energy. Now we will go further from this equation to derive what is now really the portion of this, what can be estimated as a portion of this total energy here, this total static energy, if you want to. We come to this name right now, and the kinetic energy. Now you have discussed in your atmospheric physics course the dry and moist static energy, right? Remember what the moist and dry static energy was? They were kind of conserved if you have a vertical parcel motion. And when there was no moisture, then the dry static energy would be conserved for this motion. And if there's moisture, then you could still derive a conservation law, but for the moist static energy. Now we want to derive this. We can derive this from these equations here. So because we can rewrite the divergence of P times V as, and I encourage you to do this by using the continuity equation. You can show that this is just the total derivative of P over rho. And there's a reason why we introduced this, plus the local derivative, time derivative of the pressure. If you insert this now in this equation here, and you add the two together, so you replace this term here using this identity, and you add the two equations together, you get that the kinetic energy plus internal energy plus P divided by density, which is P times the specific volume, plus the potential energy. And we know that this is just the Legendre transformation, no, in thermodynamics. So internal energy plus P times specific volume is the definition of the enthalpy. So we have kinetic energy plus enthalpy plus potential energy. That has to be equal to the right-hand side. Now, the dry static energy then, as you can see, is not a conserved quantity. However, if we have an adiabatic reversible processes, then all the friction terms are of course 0. Those drop out immediately. then if we are kind of in a situation where we have nearly hydrostatic conditions, then the kinetic energy here, changes in the kinetic energy, are to be considered small with changes in the potential energy and enthalpy. So also this is not zero, but it's kind of small. So it's kind of almost zero. And the same is true for these local pressure changes. They have also to be assumed to be small. In that case, then the dry static energy becomes a conserved quantity following the motion. But you can see there are some conditions here that should be verified. The kinetic energy change cannot be large, and the local pressure change cannot be large. But this is more or less consistent with the hydrostatic equation that has been done in the thermodynamic course when this was derived actually. Now for moist processes, if we are in the moist atmosphere, we know we can take moisture into account by adding this the latent heat of condensation times the change of the specific humidity. And that takes moisture into account. And then we get the same conservation law valid for the moist static energy. So the moist static energy in this case would be also conserved for adiabatic reversible processes, and if the local pressure changes are small, and if the kinetic energy changes are small. So we get back kind of these laws that we have derived already, or that you have derived already in the atmospheric physics class. But it's clear that neither the dry nor the moist static energy conservation laws are exact. They rely on the validity of the hydrostatic approximation, which come into play here in several places. So only if our flow is nearly hydrostatic, then we may have the conservation of the moist static energy and dry static energy. Now we come back to our original equation. We look again at the equation for internal and potential energy, and we simply use a trick. We subtract some kind of quantity on the left hand side here that just depends on entropy. And we do the same on the right hand side. So we add again a zero quantity. If our QS is defined by just an integral of some temperature that just depends on entropy, and then we integrate in this entropy space, then this is just an identity. So we have done nothing essentially. And it turns out, if we can control our system like in the engineering world, if we can control, for example, that we have an isothermal process, so then this temperature, this kind of temperature identified here, could be just the temperature, that if isothermal, then all the temperatures are the same temperature. Then it turns out that this quantity that has been defined here is U minus Ts plus phi. And then this U minus Ts would just be the free energy that has been derived as the energy available for isothermal processes. So it is clear now that this trick kind of includes this special case of isothermal processes, but is more generic because we can have some kind of temperature here that is not just constant, but can be a function of entropy. Yes, and now something complex comes into play because we have to make use of a thermodynamic property of internal energy. And this transformation that we'll be using is called is the Exergy transformation, that is based on a property of internal energy. Because if you look, and this is shown in this diagram, how internal energy varies with its canonical variables, entropy and specific volume, those are the canonical variables of internal energy, then you will see that in this space, internal energy is a convex function of its variables, entropy and specific volume. Just as kinetic energy is a convex function of the velocity. It's just quadratic. There it's very easy. Convex function, quadratic is a very easy function. But the internal energy is, of course, a very complex function, including exponentials and so on, is a very complex function of entropy and specific volume. But you can show that if the local thermodynamic equilibrium assumption is valid, so we can always divide our atmosphere into small boxes where we can apply thermodynamics in principle, then the internal energy has to be a convex function of entropy and specific volume. So this is what we will always assume when we do apply thermodynamic to our macroscopic system. And if that's the case, if we have a convex function, we can always define a tangential plane, like the one indicated here, and we can show that the difference between these two, the difference between the real energy and this kind of energy defined by this tangent plane, that difference is always positive. And this is what we want. We want to derive an energy quantity that is always positive definite. And that can be derived by subtracting from our total energy this tangential plane. Of course, for kinetic energy, this is trivial. We don't have to subtract anything. That tangential plane could be just a zero, because kinetic energy is already a positive definite quantity. So if we apply this transformation to the internal energy, we would get to a quantity that is called exergy in technical thermodynamics, and that is used to quantify how much energy could be available to convert into kinetic energy. For the atmosphere, so that would be that would be useful for small systems, for systems that are the size of laboratory experiments. But for the atmosphere, the situation is a little bit more complicated, because we have to take into account the fact that we can have a vertical stratification in our system. And therefore, we cannot apply this quantity, this transformation just to the internal energy, but we have to apply it to this quantity here, where we take also into account the potential energy and have subtracted this, what is potentially the unavailable energy reservoir here. So if we apply this transformation to this quantity, we get to the available, what is called available potential energy. And this is just, in order to do this, we have to identify a reference state, and the determination of that reference state is very important. So the deltas here would be the deviation of any quantity from the reference state quantity. That reference state would be, that reference state would be referring to such a situation. So the final state. So if this is kind of our initial state that we want to evaluate, this reference state that we want to apply would be this final state where we don't have any energy available, but it's still there's still a stratification of temperature and pressure and so on in this situation. But we have to define this reference state. Now, the nice thing about this quantity, we don't see it here yet, But this quantity here is locally positive. So wherever we are in the atmosphere, you can show that this quantity is positive, and this will be shown now. Because if you calculate the first order approximation of this quantity in terms of a Taylor series expansion, and the first order term is already by far the largest term, then we see that this available energy quantity is just a quadratic function of its variables. Just like kinetic energy is a quadratic function of the momentum. However, this quantity, whereas the standard exergy quantity used in technical thermodynamics is always positive, because we have based it on the internal energy, which is always a convex function. Now we have based this transformation on a slightly different function. And it turns out that this available potential energy quantity is only positive if we are if our reference state situation is stable. So exactly like what we have looked at here. The warm air or the warm water has to sit on top of the cold water. If we could also imagine we have the opposite situation. Where the cold water is on top of the warm water. There are also no horizontal gradients. And we have also a hydrostatic situation here probably. But that wouldn't be stable at all. There would be immediately mixing going on. The cold water cannot stay on top of the warm water. It's not a stable situation. So we can only use reference states that are stably stratified, and that comes back into this available energy expression here. So then this quantity is positive, only if we are in a stable reference state. Now you can derive evolution equations for this. So the kinetic energy essentially doesn't change. The kinetic energy equation doesn't change, obviously, but we can introduce the reference state also thereby inserting essentially zero terms on the right-hand side, and we can slightly reformulate this conversion term then into the available potential energy. And the available potential energy equation becomes also interesting, because if we insert for the T dt by ds, what is usually abbreviated as the added heating, the heat added to the system, then we can identify something that is known from technical thermodynamics as a Canoe factor. So there is this factor T minus T naught divided by T, which gives us the what we call the Canoe efficiency. So you can show also again that this Canoe efficiency in a first order Taylor series expansion is mainly governed by the temperature difference between our reference state, between the real state and our reference state. And a small contribution also from a pressure term here. But this essentially means, this is a very important result now, that what makes us gain available potential energy is the correlation between heating and Canoe factor, which means the correlation between heating and temperature deviation. So assuming that the reference state is somewhere, has a zero, it gives us a zero perturbation somewhere in the mid latitudes, and positive, it's warm at the equator and cold at the exotropics, then we come to this conclusion that we have to heat at the equator and cool at the pole. So we have to heat in order to gain available potential energy. We have to heat where it's already warm and cool where it's cold. If we do the opposite, we destroy. Of course, if we cool the warm air or warm water here and we warm the colder, then we destroy available potential energy. It's very intuitive. So now Lorentz has then taken this expression and integrated it over the whole mass of the atmosphere. And if you do this, you can reformulate this a little bit further and show that then for the whole atmosphere, integrated over the whole atmosphere, there are just two terms that remain. And he also uses the fact that we are in a quasi-hydrostatic atmosphere. So he uses the hydrostatic balance approximation and that derivative. Then we get to two terms. One is our Canoe factor multiplied with the heating. So this we have interpreted already. Only if we heat where it's already warm, we generate available potential energy. But what is this second term here? In the pressure coordinate system, okay, P is just an independent variable. So it's the correlation of temperature and vertical velocity that makes us transform. This is the transformation term of available potential energy into kinetic energy. You can show that in the kinetic energy equation, if you integrate that again over the total volume of the atmosphere, you get the same term with opposite sign. So it's the correlation of temperature with the omega vertical velocity that gives us the conversion into kinetic energy, in the sense that when we have a warm air, we have to have a negative omega. Negative omega means rising motion. So warm air has to rise and cold air has to sink in order to make this term always negative. So we can convert available potential energy into kinetic energy. So again, that is consistent with the intuitive, our picture. The cold air has to sink, or the cold water, or the warm water or air has to rise. And if you remember, one of our very first pictures, where our cyclones developed, that is exactly what is happening in our exotropical cyclones. In exotropical cyclones, the warm air is taken from the tropics and rising to the north. And we understand why there's this tendency of rising motion, because if we conserve potential temperature, then if our flow is approximately confined between two lines of constant potential temperature, then the air has to rise as it goes to the north, and it sinks as we go to the north, to the south. So we have the cold air sinking. So that will, in these cyclones, converge available potential energy into kinetic energy. This will be always happening. But interestingly, we have seen another situation where that also was the case. If you look at our stationary high pressure systems, even there, take a picture of that. Where was it? Almost there. Even here. So we discussed, we have this in the mean boreal summer season here. We have this mean high pressure system sitting over the oceans in the North Atlantic and the Pacific. And we see that in fact on this side here, on the eastern side, we have cold air flowing to the south. And we see that it's sinking because there's suppressed rainfall. That means the air sinks. Whereas on the western side here, we have rainfall. That means that the air is rising. So even in these systems here, there is a clear tendency for conversion of available potential energy that is stored in the mean temperature gradient and kinetic energy. So even these large-scale systems permanently convert available potential energy into kinetic energy. This is what the atmosphere is doing in all Rossby waves, in all developing Rossby waves, for example, in all developing or propagating or stationary systems. Now, in order to look into more details into this general circulation energetics, what people have done is, since we have now a quadratic quantity, so available potential energy is a quadratic function of temperature and pressure, and kinetic energy is a quadratic function of velocity. That means we can derive for the large scale circulation mean quantities that are defined by the zonal mean, and eddy quantities that are defined by deviations from the zonal mean. So just as we have done in some of the previous sections already, so we define zonal mean quantities and deviations from zonal mean. That can be done. And then some researchers have estimated what is the energy conversions between now we have mean kinetic energy, eddy kinetic energy, mean available potential energy, and eddy available potential energy. And so looking at observations, people have made estimate how does it look like in the atmosphere. So it seems that the main gain of available potential energy is in the mean available potential energy with the 0.5 petawatts, so a huge amount of energy that goes into there. So this is the heating at the equator due to the differential solar heating, the heating at the equator or in tropical regions, and the cooling, relative cooling in the northern regions that brings this, that increases this available potential energy reservoir. Now, most of this is then transformed into eddy available potential energy. So these are our waves that are generated, the Rossby waves that are now eddies. They can be stationary or propagating. These Rossby waves, these perturbations from the zonal mean, they gain energy in this case, in this interpretation, first transforming this mean available potential energy into this eddy available potential energy. Then while doing this, there's some more gain. Now this gain is probably due to the fact that in our Rossby waves, we have heating, condensational heating in regions and cooling in other regions. So there's some addition of the energy then coming due to the condensational heating processes also in our Rossby waves. And then this is all converted into kinetic energy, into eddy kinetic energy. This is the main conclusion here. This is then converted essentially all into eddy kinetic energy. So the energy contained in our propagating and stationary Rossby waves, this is what we see here. And most of this energy is dissipated. So the cyclones and anticyclones, Rossby waves that propagate, they gain energy from the mean state. They gain energy from this transformation. But then they are so powerful that there's a lot of frictional dissipation going on. But not all. Because since our main energy gain is for the eddies, there is the possibility, which is very counterintuitive for people who are used to think of small-scale turbulence, that eddy kinetic energy is transformed back into mean state kinetic energy. But that is the case for the large-scale circulation. As you can see, this is only possible if our main energy source is in the eddies, in the large-scale eddies. Then we can transform a little bit of that back into the kinetic energy reservoir. This will never happen for classical turbulence, because there the energy gain is at the very large scale, and then we have the smaller scales that gain energy from the large scales. But for what we call the geostrophic turbulence, we have this a little bit counterintuitive result that we can actually transform back energy from our huge kinetic energy reservoir into the mean eddy kinetic energy, into the mean kinetic energy reservoir. And this transformation is consistent with what we have seen for the jets. Because in the jets, we have seen that these eddies that propagate away and propagate energy away from the jet, they actually transport mean momentum into the jet. So that comes back here now in terms of energetics. And then these errors are probably relatively uncertain. So then part of that is simply dissipated again. But part of this may be also again feedback into the available potential energy. So that could be the case if for example, the frictional dissipation heats more regions that are already warm, then we could have this feedback onto the mean available potential energy. But I believe that this is a relative small value compared to the others. So maybe the sign of this is not very clear. Now, the reason I think that the atmosphere is so exciting is we look at the ocean, and now Ricardo would be probably very angry. But at least the energetics from a very, let's say, this is a very simplified way to look at the ocean energetics. But this is the energetics of the main ocean circulations indeed, is that the main of the energy generation at the ocean is just mechanical generation at the surface. So most ocean flows are generated directly from the kinetic energy that is driven by the surface stress at the surface. And then most of that is simply dissipated. So there's this flow here from energy generation at the surface, and then that goes into the ocean moves, and then things are dissipated. There is some kind of indication, but the signs are probably not clear, that there is a conversion also possible from available potential energy into the kinetic energy in the ocean. Now, this is certainly the case for these thermohaline circulations and so on, but they are so slow, and so the kinetic energy and the energies in general involved in those very slow circulations are so small compared to the large directly forced, wind-forced ocean circulations that energetically they don't come out very much in this diagram. So I think it's not even sure if this arrow goes in this or in this direction. So people are not yet sure about this. Could go both directions. But maybe if we filter out between just the wind-driven circulations and the much slower thermohaline circulations in the ocean, then maybe this exchange between available potential and kinetic energy, that would show up much more clearly, and there should be some kind of energy cycle, more interesting energy cycle also in the ocean. Okay, so in terms of exercises, I encourage you strongly to do the first exercise. This is a very interesting exercise. And there's a small hint that you have to do partial integration. So please try to do this first exercise. The second exercise you don't have to do. So the next lecture, then we will look at a moisture budget equation, which is also very important, and its application, for example, in that case, just to the Sahel drought, but it can be applied anywhere. And I think we will also have to do 2 lectures on Wednesday in order to be able to finish this week. Okay? See you on Wednesday then. Bye.
Bye. Bye.
Bye. Thank you.